in season 2, we are going to focus on the chemical reactions. We want to know what exactly, the reason why the reaction is happening and why it's happening in that way, right? Including, how much heat it will absorb or release, how fast the reaction is, if it's reversible, how favorable it can go to a certain side, and if it's a redox reaction, what will be the special property of the reaction. So this is the general topic of season 2. So I strongly recommend you to turn your camera on and feel free to jump in if you have any question. You don't have to leave it to the end, or you don't have to reserve your question. Okay. So today we are going to start from thermochemistry. I slightly revised our schedule. I put the thermodynamics a little bit later after the equilibrium. So thermodynamics are slightly different. Thermochem focus on the heat, right? So this will be the first part. Okay. The first question is about calorimetry. Let me find my pen. Okay, calorimetry. Basically, the meaning of calorimetry is the measurement of heat, because the word actually is from calorie, right? You know this word? No, this is not right. Calorie. How to spell calorie?
I-E.
Ah, interesting. R-E?
I-E.
Ah, thank you. Wow. It doesn't look right to me, but anyway. So this is the unit, used to measure the heat, right? And 1 calorie actually is 1.8 joule. You will figure out why there is a conversion like this later. So this is the meaning of calorimetry. So the calorimetry is built on an equation Q equals to Cm delta T. So we will briefly talk about what is the meaning of each parameter here. Q is the heat. Delta T is easy to understand. That is the temperature change, right? Is the temperature increasement or decreasement. So the delta T can be positive or negative, depends on the situation, right? M is the mass of the solution or the mass of the substance in the system, right? So I think these two are relatively straightforward. And the C is called specific heat. What is the meaning of specific heat, guys? It means if the mass is 1 gram, the delta T is 1 degree Celsius or 1 Kelvin. Basically, 1 degree Celsius equals to 1 Kelvin, right? And then the heat, absorbed or released is called the specific heat of the substance, right? So I think it makes sense. So it's a constant. It is a constant for a specific substance. What does it mean? So which means for a specific substance, the C is a constant, is not related to the mass, is not related to the delta T. But if it's not the same substance, let's say water compared to carbon dioxide, they will have a different constant here, right? So you probably know the specific heat for water is 1.18 joule per degree Celsius per gram. So this is why 1 calorie is 4.18 joule. So it just depends on how you define, the energy, right? So if we define for water, 1 gram of water, the temperature increased by 1 degree Celsius, how much absorbed is called 1 calorie, and then you will get 1 calorie is 4.18 joule, right? Make sense? Okay. And then another important equation used here is called Q input equals to Q output, which means we suppose there's no energy loss, there's no heat lost. All of the energy released from the hot substance will be absorbed by the cold substance. So all of the calculation is built on this equation. Oh, by the way, I need to remind you, you need to have a periodic table with you all the time, which is easy for you to check. You can get it from either a textbook, or a better idea is you have a larger either printed one or handwritten one put on the wall you are facing, right, for you to check easily. That would be the best, because we need to use it all the time. And secondly, for this season specific, we need to have a scientific calculator with you, a non-programmable scientific calculator, because for this one we'll have a lot of calculations, which is time consuming, but we do not have so much time for you to just do the calculation in the class. But we cannot skip this kind of processes, because this is something you need to build. Okay, let's have a quick look about the question. Okay, I will now read the question, so you guys can do a quick reading, and then we'll briefly talk about the question. I think you probably finished the reading, right? So I will leave time for you to try some practice by yourself. So the Q input here, is the cold substance, which is the deuterium oxide, right? The heavy water. And the Q output is the heat released by the hot substance, which is the uranium metal, right? So for both of these two Q, we can apply the Cm delta T. So now I say this is C1 M1 delta T1. This is C2 M2 delta T2. So these two should be equal to each other, just with a sign difference, right? Or you can say the sum of these two Q will equal to 0. Make sense to you? Okay, so I think we just need to put the parameters in. So the C1 is here, which is 0.117. I will recommend you to put the unit in your calculation. This is the C1. M1, we don't know, but we know it's a cube. And then we know the density. What is the density of the uranium, which is here. And we are looking for the length of the edge. So I think it's easy for you to understand. The volume equals to the edge to the power of third, and the mass equals to the density times the volume, right? This is some fundamental physics. So we can put this in because we want to get the mass. The mass will equals to the density, which is 19.05 gram per centimeter cube, times the volume, which is 8 cubic, and then equals to, times the delta T1. What is delta T here? The final temperature here, the initial temperature is here. So it will be final minus initial, right? And then equals to negative C2, which is here, 4.211 joule per degree Celsius per gram, times the mass. What is the mass? Is 1.00 liter, and the density is now 1, is 1.11 gram per milliliter. So we can convert this into 1.00 times 10 to the power of third, change into milliliter first, and then multiply by the density, which is here, and then multiply by the delta T, the delta T2, which should be the T final, 28.5 degrees Celsius minus the initial is here, 25.5 degrees Celsius. So as you can see, that is a long equation, right? So it's really a good assessment for your skill in pressing the scientific calculator, because it's like typing, right? So you really need to use the the same scientific calculator all the time, because you need to be familiar with, the calculator. Otherwise, it's very easy to make mistakes. But mathematically, it's not a hard question, because there's only one parameter, right? One unknown, and all of the other stuff are, is known. And the only thing you need to pay attention is the significant figures, right? And also the unit.
Wait, Dr. Chen.
Yeah.
Isn't the answer missing a sig fig?
Let me check. This is a good question. I don't think so. Do you know why?
No.
Check the last parenthesis.
Yeah, if you cube it, right?
Check here.
Oh, okay, yeah, it's 3.0.
Yeah, 28.5 minus 25.5 equals to, this part only equals to 3.0, right? So there are only two significant figures. So which means during this process, there is one significant figure lost, right? Because I think you understand the meaning of significant figures, right? This is estimated, this is estimated. So in your final results, this 0 is also estimated, but you only have one significant figure before the decimal point. So, the limitation is here. So the final results will be followed by this number 3.0. So this is why your answer has only two significant figures. So you guys can, either check it right now quickly or leave this as your homework. I show you the method. The remaining parts is just some, I think, relative simple math. But pay attention to the unit and the significant figure, because the a cubic need to cancel the unit here, centimeter, cubic. So this is why your answer has a unit of centimeter, right? I'm not sure how confident you guys are about the fundamental physics part here, but I think if you take some time, think about, it should be fine, right? Any question about the method of this question or the general idea of calorimetry? Okay, great. Alex, did you finish the calculation?
Yeah, it was 3.3.
Okay, great. Yeah, I saw a few of you, already finished the calculation, which is good. Yeah, I encourage you guys can kind of, finish everything before me, right? And then you can check with my answer. Yeah, this question is a little bit different. So we can have a quick look. We probably don't have time to show the full work here, but you guys can read it, and then we can talk about the general method. You don't have to get the final answer, but I will give you a little bit more time for you to figure out what is the method. You set up the equation and you think about how you can get, the enthalpy. The enthalpy basically means the heat change per mole of barium sulfate form. So the question is asking you, per 1 mole of barium sulfate, how much heat is released? So which means after you finish the calculation of Q, there is one more step. Because this Q, this heat, is now responding to 1 mole of precipitate, right? It's responding to a certain amount, which needs to be calculated by this. So this is why I skip something here for you to think about, because this is related to stoichiometry, and you need to figure out which one is the limiting reactance. So in general, for this whole season, my job, for a lot of my job, I would be a math teacher. I hope, you guys don't need to be taught, from me regarding the math work. Okay.
Dr. Chen.
Yeah.
I have a question. So when you're doing the density of the final solution, are you assuming that the precipitate has already left the solution or that it's still in solution?
It's a good question. I think this is something, we are not very clear in the question. So what we did is, first, we suppose the final volume is just the sum of the 2 parts of the solution, right? So I don't think there is a lot of precipitate form. So I think this assumption should be valid. So the volume will not change too much. Okay. And this is the only way we can work on this. So it really doesn't matter, the density of the solution includes the precipitate or not, because we are going to, ignore that part.
So then, what if we were doing a stoichiometry question, how would the final answer change if you actually assume that the volume would change?
I don't think it will change too much. If there is no, specific, sentence talking about how the volume will change, you can assume it's just the sum of the 2 parts, the volume, final volume. So the reason why I multiply by 1000 is because we have a dimensional analysis, right? Later to be milliliter, because the density is always in gram per milliliter, but the volume is typically expressed in liter. So this is something you need to pay attention. By the way, for delta T, please always use T final minus T initial. So which means the final temperature minus the initial temperature. This is definition of delta, right? Delta means the final states minus the initial states. So you don't need to care about the sign. The sign will be given by the T final minus the T initial. So if this is the way, you will get a positive, Q with a unit of a joule, right? Is a positive value because delta T is positive. But actually, when the temperature is increasing, it means the reaction is exothermic. Am I right? Exo means it releases energy, and then that means the delta H is negative, because the energy released from the system actually is the heat absorbed by the solution, right? The reason why the temperature of the solution will increase is exactly because the heat is released from the reaction system. So the reaction actually loses energy, or the reaction system loses energy. The energy is from the precipitation process, right? So this is why the delta H equals to negative Q, right? Negative Q. So the final answer, the sign plus or minus shows is a exo or an endothermic reaction. You also need to pay attention. You need to calculate how many moles of the precipitate is produced here. So I skipped one step. You need to figure out which one is the limiting, reactance, right? So let's calculate here. So the skipping part will be the moles of the sodium sulfate will be 1.00 liter times 2.00 mole per liter. So it will be 2.00 mole. And the moles of the barium nitrate will be 2.0 liter times 0.75 mole per liter, which will be 1.50 mole. So as you can see, the second one is the limiting reactance, which means the amount of the precipitate will be determined by the limiting reactance. So this is why I directly put, the amount of the barium nitrate here, right? Because it equals to the amount of the barium sulfate, and then you will get the final results. Any question about the method, the general idea here? Is that all good? So if you have a question like this, will you be confident, to solve it? Okay, great. Let me know if you have any further question. If you didn't get the time to finish in class, it's totally fine. You can take some time after class to do the calculation part. But I want to emphasize the calculation part actually is very important, because the USNCO for most of the parts is a multiple choices based competition, right? So which means no matter how accurate your method is, if you couldn't get the final correct answer, it's still 0, right? So this is why it's critical. Okay, so this is the general method for calorimetry. But there are some questions which are a little bit more advanced because it includes the phase change. For example, you put some ice into some hot water, right? The hot water, will be cooled down. The ice will be warmed up. So it first will be melt into liquid water, and then the cold liquid water will further be warm, turned into a hot water, right, or a warm water. So basically, there will be a phase change included. So you just need to add the energy needed for the phase change into the calculation. So basically, for most phase change, I think it will be endothermic in these kind of cases. For example, the melting process. So you just need to put this part into the Q output, right? Sorry, let me see. Yeah, I think so. The Q input is the heat released from the hot substance, right? And the Q input is the Q output will be the heat absorbed by the cold substance. So I put something here. There are a few abbreviations. Fusion means the melting process. Vaporization is easy to understand, right? This is from solid to liquid. This is from liquid to gas. This is sublimation. So basically, it's from the solid to the gas directly without going through the liquid. So I think this equation makes sense too, right? The total energy is the sum of the fusion plus the vaporization. So we have the heating curve here. Basically, is how does the temperature change when the heat is added to the substance? First, it will be a solid, right, initially. And then when heat is provided, it will absorb heat, and then the temperature will increase, and then there will be a flat area. This is the process of the melting or the fusion process. So you may need to think about why during this process, the temperature does not change with heat. That's because the heat is used to overcome the intermolecular forces here, right? So this is why there will be a flat stage with no temperature increasement. And then after all of the solid is melt, so it changes into liquid. And then if you continue to heat it, the temperature will increase. And then there will be another flat area. This is the process of vaporization. And then it will be further increase. So this is called the heating curve. And if you pay attention to the y-axis, the temperature here is the freezing point or the melting point. The temperature here is the boiling point. I think this is for water, right? Because at atmospheric pressure, water has a freezing point of 0 degrees Celsius and a boiling point of 100 degrees Celsius. It also shows the delta H for the melting process. Wait a second, which is not here, which is here. The delta H of the vaporization process. This heat is a little bit problematic because, okay, it's kilojoule per mole, which means for 1 mole of liquid water, if you increase the temperature from 0 degrees Celsius to 100 degrees Celsius, the heat needed will be 7.3 kilojoule per mole. I want to double check because there's no phase change during this process, right?
Hey, Dr. Chen, I just checked it. It's correct.
It's correct? Okay,
Yeah.
great. Let me have a quick check. Cm delta T is 4.18 joule per gram per degree Celsius. And M for 1 mole of water, you guys know what is the mass, right? 1 mole of water, it will be 18.0 gram, right? So I skip one step to show how to calculate the mass of 1 mole of water. And the delta T will be 100 minus 1 degrees Celsius. So you guys can check the answer to see whether it's 7.3 kilojoule per mole or not. I think it should be fine, right? Thanks, Alex. Okay, this is a real US NCO question from the local 2012, number 20. So let me see. Is there phase change involved? It seems like there's no phase change involved. I think I made a mistake, but it's fine. We can work on the question. So we'll provide a polling and give you around, let's say, 1 minute, maybe. My polling not working. Interesting. You guys can work on the question right now. Okay, it is working. So let's have a race to see, you are fast or I'm fast, okay? I think I put a wrong question here. I should have a question related to phase change.
Dr. Chen, you forgot a negative.
You're right. Yeah, feel free to use your calculator. If you finish, you can search in Google by yourself to find this question to practice. Local 2016, question number 21. Okay, guys, we have to stop here. I think the question is pretty straightforward. The time-consuming process is the calculation, right? So you list the equation and you solve the problem. Very good to see, 6 of you and more students actually are submitting. Let's stop here. You all got the correct answer, I believe. Let me share the results with you. All of the 7 students, chose the answer. If you didn't finish, take some time after class. Okay. Yeah, because we have around 10 pages to cover. So which means averagely, how many pages we need to finish in 30 minutes? 2.5 pages. So I think, yeah, we are close, but we need to continue. Okay, the next part is about the equipment used to measure the heat, which is called calorimeter. So it's still from the same word, calorie, right? So we have 2 types of calorimeters. The first one is called coffee cup. The second one is called bomb calorimeter. The coffee cup actually is pretty easy to understand. Basically, is when you go to the Starbucks or any other coffee shop, you buy a cup of coffee because it's so hot, right? So you have another cup, to put on it, right? So basically, it's a kind of 2 layers of cups, and then this is why it's called coffee cup. And the 2 layers is to provide heat insulation, right? Because we suppose the air in between the 2 layers of the cup will be heat resistant. So we assume there's no heat lost during the process. So we have an inner cup, we have an outer cup. So the reaction will be in the inner cup, and the outer cup, is either for you to hold or just put it there for the heat insulation. And then we have a stirrer, because you need to speed up the reaction. You have a thermometer. Typically, the cups are made by polystyrene cups because it has a relative good heat insulation effect. And then if you further pay attention to the stirrer, it's a kind of ring stirrer because it's different from the glass stirrer. The glass stirrer is you will stir in this way, right? You stir in this way. But for this one, you will stir in this way. You will put it up and down, and then this ring will help the solution to mix with each other, right? Because if you want to stir in this way, it's very hard for you to put the cap on because you need to put the cap on, right? To further prevent the heat loss, right? If you just leave it open, it's very easy to lose heat. And you want to, maintain all of the heat in the cups. So this is called coffee cup. So the application for this type of calorimeter is to measure the heat of a certain reaction, especially the reaction in the solutions, in the aqueous solution. For example, the neutralization. So the neutralization reaction, right? This is a good example. But think about if we have a reaction like this. Let's say you have zinc solid react with hydrochloric acid, it will produce zinc chloride, aqueous, and hydrogen gas. Think about, will this be a reaction which can be measured by the coffee cup calorimeter? If not, what will be the reason why the coffee cup will not be a good one, a good setup to measure the reaction heat for reactions like this? Or I can give you one more example. So let's say you have methane, which is a gas. We burn it in the oxygen gas, and then it produce carbon dioxide and water gas, and then we balance it to here. How about these 2 reactions? Can we still use the coffee cup calorimeter to measure the heat for reactions like this? What's your idea?
I don't think it would be good for the second reaction for sure because you have gases, so it'd be hard to keep them in the cup.
A very good point, right? So if you have a open system, a relative open system like the coffee cup, you cannot contain the gas in the system, right? And when the gas is released, the gas actually bring the heat, right? So this is why you cannot use the coffee cup to measure any reaction with heat involved, with gas involved or gas released. So this applied to the first reaction because it also produces gas, right? No matter it's axial or endothermic, the gas will also bring the heat. So this is why we need to have the bomb calorimeter. If you have a look at the structure, there is a bomb inside. The bomb is a kind of closed system, and the bomb is put into a water bath. And then we can put the gas or the reactants in the bomb in advance, and then we can use the electricity to initiate the reaction. For example, it's combustion or any other reaction. Actually, it's pretty good for combustion because you can use the electricity to ignite the reaction, and then the reaction will occurring in the bomb, and then the bomb will be heated, be warm, and then the heat will be released. Sorry, the heat will be absorbed by the water bath. So this is why your thermometer actually is put in the water bath, not in the bomb, right? You cannot put a thermometer in the bomb because there will be a combustion, an explosion in the bomb, right? So this is good for the measurement of combustion. Typically, the bomb calorimeter is not as important as the coffee cup one, but I listed here for you to have a comparison. So different type of reaction need to use different type of setup or equipment to measure the heat. And you also have a stir because you want to make sure the temperature is universal in the system, in the water bath, right? So everywhere has the same temperature. Okay, good. Let's have a look at this question. Yeah, the good news is not a calculation, so we don't need to put too much time here. But it's related to conception understanding. Have a quick read and check your answer. Wow, I got 3 votes, all different answers. So I can tell, this year it will be very challenging for preparing the USNCO because, you guys, most of you probably didn't get the chance to really work on the experiment in your school, in your lab, right? So the experimentation will be a big challenge. So I will, try to implement different methods to enhance your understanding. But if you can get, opportunity to work in the lab, that would be better. Okay, give you 15 more seconds. We got 13. $14 votes. Think about, for an endothermic reaction, the calorimeter, the cup, the coffee cup will feel warm or feel cold, guys?
Cold.
It will be cold, right? Because the reaction absorbs heat. So where is the heat from? It's from the solution first, and then further from the cup, right? So you'll feel it's cold. Okay, great. Let me show the answer to you. Very interesting, right? 7 students out of 14 chose C. C actually is the correct answer. Why? Because if, what the question is asking about, neglect to put a lid. So if the student forgot to do this, the heat will be absorbed from the air, right? From the environment to the system, which will decrease, which will reduce the delta T. Previously, NASA, it changed from, let me give you an example. So NASA, the room temperature is 25 degrees Celsius. If everything is good, now say the temperature will decrease to 20 degrees Celsius, okay? So it will be slightly cooler, but not too cold. But if you forgot to put a lid on the cup, which means some heat will be absorbed from the environment, from the air. So the final temperature will be higher than 20 degrees Celsius. Probably is 22 degrees Celsius, which means when you calculate the Q equals to Cm delta T, the delta T, the absolute value of delta T actually is smaller, right? Pay attention, it's asking the magnitude, so you don't need to worry about the sign. Although the delta T here is negative because the heat is absorbed, but the reaction actually is absorbing energy, right? So this is why the answer is too small. The solution will absorb heat from the room or from the environment or from the air. Does this make sense to you? A very interesting question, right? Guys, let's have a quick revolt. If this reaction is exothermic, so the options are still the same. Guys, let's watch for one more round. Give you 30 seconds. So the only difference is the reaction is exothermic. Right, 10 more seconds. Okay, great. Much better, right? A is the correct answer. It will be still too small because some heat will be released into the environment, so which means the final temperature will be lower than expected, right? So which means the delta T is still smaller in magnitude. So the final Q is also smaller than the expectation. Does this make sense to you? Okay, great. Let me see. I can think about any other stuff here. Nope, I think we are good. Yeah, I think this is the real experiment, how to use a coffee cup calorimeter to measure the neutralization enthalpy. Basically, it's the neutralization heat. Could you please also quickly list the equation? But if you have time, solve the equation. If you don't have time, leave the equation there, okay? The difference between the Q and the delta H is the delta H need to consider how many moles of water is produced. I think I made a mistake.
I don't think you
question,
did. I think you're right, because I got the
I'm
same
right.
thing. Yeah.
So this is why I said I made a mistake, because the question was fabricated by me. So I fabricated all the data, but obviously the final answer is too big, because the theoretical value is 1 magnitude smaller. So I think I should say this is 1.00 molar. This is also 1.00 molar. And then we can change this into 1.00 molar, and then change this into the power 4. And finally, it will be 52.3 kilojoule per mole. That will make more sense. But since this is just an example to show you, guys, you can make the change by yourself.
I think it should also be 2 sig figs because of 26.1 minus 20.0.
Very good point. Thank you. Give me one. Yeah, so this is 6.1. So we should change our answer here into 5.2, 5.2 as well, 5.2. So the final answer will be negative 52 kilojoule per mole. Guys, please make the change here. Here, it should be 1.00 mole per liter. Yeah, if you didn't get the final answer, it's totally fine. But I want to take some time to talk about the percent error. What is the definition of the percent error? It's defined as in this way. So your experimental value minus the actual value divided by the actual value times 100%. This is the definition, how we define the percent error. So this is the error, and then divided by the actual value, this will be the percent error. So if we put the data in, it will equal to negative 52 minus negative 57.3 divided by negative 57.3. So times 100%, we will get a negative, right, percent, a negative percent. That means your answer actually is smaller than expected, right? A negative, error means your results is smaller than the expectation. What that further mean? So which means it should release so much heat, but actually your measurement only gave you, 52. So which means some heat actually is lost during the process. This makes sense because the coffee cup calorimeter is not 100%, heat resistant, right? The value is supposed to be lower than your expectation. Okay, I think this question should give you a good sense about how to calculate the delta H. So basically, if you see a delta H with a subscript of M, the M means per mole. It means 1 mole of reaction or 1 mole of products. So basically, it's asking a different unit. It's not joule anymore. It should be joule per mole. And here, since it's a neutralization, so we are asking, how many moles of water is produced. And why we use the acid to calculate the moles of the water, that's because the base is slightly in excess, right? 100 milliliter compared to 105 milliliter. Makes sense to you, right? Okay. Let me see. So we'll finish 2.1 and then we'll take a 5-minute break, okay? So next part is the reaction enthalpy and the Hess law. So we can, talk about the meaning of each letter here in a more systematic way. The delta is clear, final minus the initial. The H is the enthalpy. Before we really talk about what is the exact meaning of enthalpy, you can say enthalpy equals to heat, okay? Although it's not correct, but right now we can understand it in this way. And then you see the R. The R means reaction. So this is for a certain reaction. Definitely the R can be replaced by different letters. For example, if a neutralization, we probably will use NEU. If it's combustion, we'll use C. If it's a formation, we'll use F. So you probably will see different letter here to represent different type of reaction, but it really doesn't matter too much. You don't have to remember, F is for formation, C is for combustion, but the question will make it clear. But those are very common use, abbreviations to show you what is the type of the reaction. So R is kind of in general for reaction. And the M here is the molar, which means for 1 mole of reaction. So what is the meaning of 1 mole of reaction? Let me write down here. For example, let's say you have CH4 reacting with O2, produce CO2 and water. I ignore the states, okay? Just want to show you a balanced equation. So how can we define a 1 mole of reaction? Is 1 mole of CH4 or 1 mole of O2 or 1 mole of CO2 or 1 mole of water? It's not clear, right? So we do not try to define 1 mole of reaction from any reactants or substance or products. We define 1 mole of reaction, which means when you write down a balanced chemical equation, 1 mole of reaction will be 1 mole of CH4 reacting with 2 mole of O2, produce 1 mole of CO2 and 2 mole of water. So next time, if a different student balance the reaction in this way, let's say 2 CH4 plus 4 O2 produce 2 CO2 and 4 H2O. So the 1 mole of reaction will be different. That would be 2, 4, 2, 4. So please pay attention how we define 1 mole of reaction. It depends on how you write the balanced chemical equation. So why I emphasize balance is they're actually not balanced. So it doesn't make any sense, right? For 1 mole of reaction, because you even don't know how many, moles of reactants are involved, how many moles of products are produced. So this is the definition of 1 mole of reaction. So the M here is for the molar delta H. And finally, the delta means the standard state. What definition of standard states? It means all of the gas have a partial pressure of standard pressure, which is 1 bar. 1 bar equals to 10 to the power of 5 Pascal. This is called standard pressure. And all of the aqueous solution is C standard, which is 1 mole per liter. All of the concentrations are 1 mole per liter. This is called the definition of standard states. So next, we are going to introduce you a few reaction enthalpy. The first one, which is also the most important one, is called molar enthalpy of formation. We use delta F, H, and standard. So I think the only new stuff is here, formation, right? How we define this? It means first, you have 1 mole product, but this product is produced from its constitutional elements. Let me give you an example. So let's say water. This is your product. So you need to use the element, hydrogen gas. You need to use the oxygen gas, O2, to produce 1 mole of water. So you will have 1 mole of H2, you have 1/2 mole of O2. So the delta HR, which means the molar reaction enthalpy of this reaction, is the delta HF of water. That's called the molar enthalpy of formation of water. So 2 points. The first one, the product is 1 mole. Secondly, you need to use the stable elements to make this product. But you probably will have a question, how will be the states of each substance here, right? Because in the definition of the standard states, we do not have temperature requirement. So please pay attention. Typically, if there is no specific explanation all of the delta H are at room temperature, which means it's 25 degrees Celsius or 298 Kelvin. So basically, we ignore this, but actually, there is something like this here. So all of the data are got at this temperature. So this is why the water is at liquid state and the hydrogen and oxygen are in gas states. So a following question will be, so what will be the delta HF of a element? How about, what will be the value, or what will be the definition of the molar enthalpy of formation of an element such as hydrogen gas?
It'd be 0.
It would be 0, right? Now this makes sense because itself is an element. So it is defined as 0. It is 0 kilojoule per mole, right? 0. But please pay attention. Some elements have different allotropes. For example, oxygen, it has O2 and O3. Carbon has diamond, graphite, carbon nanotube, graphene, and a lot of different allotropes, right? So which means not all of the elements will have a molar enthalpy of formation to be 0. You need to pick up which one is the most stable. Think about, if it's oxygen element, which one will be 0 kilojoule per mole, the O2 or the O3?
O2.
Should be O2, right? O2 is more stable than the O3. And then if you check the data, the ozone, the O3, will be a positive value. It will be positive. So it comes another question: what is the significance of the sign of the delta FH value? So now I say, what does it mean for ozone to be, positive? Does it mean the ozone is thermodynamically more stable or less stable?
Less stable.
It is less stable. How can we justify this? Let me write down the change from O2 into O3.
Because nature prefers exothermic reactions, so nature prefers negative.
Exactly, right? So as you can see, this process will be endothermic, right? If you change O2 into ozone, it will absorb energy, which means the energy profile will be like this. O2 is here, O3 is here. So which means O3 actually has more energy, has a higher energy than O2. Higher energy means unstable, thermodynamically unstable, right? It's kind of, if you are standing in a third floor, actually you are more risky compared to you are standing at the second floor, right? Kind of, analogy. Okay, let's have a look at this question to test your understanding about the new concept. It should be pretty quick because there's no calculation involved. Okay, 15 more seconds. Hurry up. Okay, the last 5 seconds. Great. Not very good. Although most of you chose B, which is the correct answer. Why C and D are both incorrect? Please remember, elements. You need to have elements as a reactants, right? So this is why B is the only correct answer. This is by definition. There's no reason to talk about this. F, formation, you need to start from the elements. And obviously C, this is not the element. Those are not the elements, right? You guys know what are elements, right? Yeah, so this is why you need to use B. Although this reaction doesn't look so good as C and D, right? But it's the correct one. It's ugly, but it's correct. Right? Typically, no people will use sodium, O2, and hydrogen gas to produce the sodium hydroxide, right? No way. You probably use, I think you probably will use A, the reaction A, to produce the sodium hydroxide, right? Sometimes it will trick you by showing, two more products. You need to pick up this, okay? It has to be one more product, okay? Sometimes it will trick you by using different states. So you need to pay attention. Typically, is in 25 degrees Celsius. You need to figure out what is the natural states of the elements and the products. Good. I will stop sharing. Let me see. Okay, we have one more question. So for carbon, we have two common allotropes. The first one is diamond. The second one is graphite. If you check the data, can someone quickly check the data for me? Actually, the delta HF of graphite is 0 kilojoule per mole, and the delta HF of diamond is positive. I remember it's plus 3 point something, but I forgot the exact value. The value doesn't matter, but we just need to pay attention. It's positive. What does it mean? It means thermodynamically, graphite actually is more stable, and diamond is a little bit less stable or unstable. So just let you know, you don't need to memorize the conclusion. Just give you an example. If you have allotropes, there's only one of them is defined to be 0, and the others either is positive. I think it should be positive because the one to be 0 should be the most stable one, right? Thermodynamically. So the others will be positive. And also similarly for a compound, if a compound have a negative delta HF, which means it is stable, it's relatively easy to produce, right? It produces heat, it release heat. But if it's positive, it means it's unstable thermodynamically. Any question before we take a break? Okay, let's restart at 9:20 from my time, 9:20. I will recommend you guys to take a walk, stretch a little bit, get some water, or go to the restroom. Don't just sit here for 2 hours. It will be very tough. The content is already very tough. I want to hurt your back, your neck, because I am doing this every day. It's really tough. Okay, take a break. See you later.
do that.
Okay, time to be back. Yeah, it will be great. You can, continue to turn your camera on. Thank you, everyone. I hope you guys, had a short but very good break. It might not be enough for you to, get some, food. Okay. Should we start? Yeah, I think teaching is a process which needs interaction, because the interaction will give the teacher and also student passion. I cannot teach without interaction with the students. If that is the case, I would rather just record, right? I'm facing the camera and talking about all the time. Probably I can save some time. A 2-hour session can be squeezed into 90 minutes, right? Which can also save you your time. So I really appreciate your very active engagement during the class, which is good for me and also hopefully good for you. Okay, let's continue. So the next topic is about the calculation of the .hr, which is the enthalpy change for reaction by using different molar enthalpy, such as the formation, such as the combustion, or even use the bound energy. And the principle behind this kind of calculation is called Hess law. We are going to talk about this later. Before we talk about Hess law, we need to introduce a very important concept, which is called state function. What is a state function? Basically, it means the states or the function is determined by the initial and the final states. It's not related to the past. Basically, not related how the final states is achieved. This is like, I only care about how many points you get in the local exam. I do not care how much time you prepare for the exam, right? That is a little bit not so good, but there are functions like this. They are called state function. So give you an example. Let's say this is the mountain. Obviously, if your initial state is here, this is you, and your goal is here, the mountain, the top of the mountain. So you can choose a way like this, which choose the most challenging pathway. So you directly climb up, right, directly. Or you can use, there probably will be a path like this, which will take a longer time, but is relatively easier, right? So what is the state function here? In physics, you will say the distance, sorry, not called distance, the displacement from the initial point to the final point is the state function, because it does not care about which path you travel. We only care about the initial place and the final place. Or you can say the height distance of these 2 points will be the state function. But the distance you traveled actually is not a state function, because it really depends which path, which road you choose, right? If you choose the longer one, it will be longer. If you choose the shorter one, it will be shorter. I hope this will give you a brief understanding about what is the state function. Actually, we can list a few state functions. Let me give you one. Let's say temperature, right? If the temperature is 0 degrees Celsius, we do not care, the 0 degrees Celsius is heated from an even lower temperature or it's cooled down, from a higher temperature, right? But if 0 degrees Celsius is 0 degrees Celsius, which means the kinetic energy of the molecule in the system will be a certain value responding to the 0 degrees Celsius, right? Can you list a few state functions?
Enthalpy?
Enthalpy is a good one, right? This is something we are going to talk. It is, right? But there is a very interesting question. So is Q a state function or not, right? We'll leave this question to pretty much at the end of this class. We'll figure out. So this is the state function. We are going to learn a few more in the following lecture notes, such as the entropy, the Gibbs free energy, and a few other stuff. So next, we want to have a look at the work. Is work a state function or not? It's related to physics, but we have to talk. So the work is defined as the force times the distance traveled. This is how we define work. So here, I will not show you the full work, how the work expressed here. Just want to give you a sense. For gas expansion, the work equals to negative P delta V. Basically, this is the pressure, this is the delta V. So if we focus on the work done during each process, let's have a look. So if we start from point 1 to point 3, as you can see, 1, 2, 3, the pressure is the same and the volume is expanding from V1 to V2. So the work will be the area here. Make sense? P times delta V, right? So this will be the work done during the process 1, 2, 3. And then if we have look at 3 to 2, this process, 3 to 2, where is it? Oh, there's no picture to show 3 to 2, which is here. So 3 to 2 is the same volume, but different, pressure, which means the delta V will be 0, right? So the W here, the work here during this process is 0, So this is the first way for you to achieve, from point 1 to point 2. So you go through this direction. So the total work will be the work done here plus 0, right? But you may have different ways. Let's say your second way is you first go to 4 and then you go to 2, right? So if you go from 1 to 4, the work, how much is the work here? The delta V is also 0, right? So which means the work here is also 0. And if you go from 4 to 2, which is this process, the work is still P times delta V, but the delta V is much smaller. Oh, I should say the P is much smaller, so the work is here. So as you can see, the work from 1 to 3 to 2 is not equal to the work from 1 to 4 to 2. So what is the conclusion I want to make? Is the work is path dependent. So it is not a state function. Because if you continue to have a look, so we can also do a path like this, which will give you a work like this. You need to use calculus to calculate the work done here. This is a little bit beyond the USNCO, so it should be fine. But just let you know, work is path dependent. It's not path independent. So it is not a state function. It is not a state function. So A, B, C, these three processes all have different, work. No worry, we are going to continue to talk about how to calculate the work in the following few, sections. Just give you a sense first. Work is not a state function. So H is a state function. So with this in mind, we can talk about the Hess law. What is the Hess law? It means the heat of any reaction for a specific reaction is equal to the sum of the heats of reaction for any set of reactions, which is in sum are equivalent to the overall reaction. What does that mean? Basically, if you can add two reactions together to get an overall reaction, the enthalpy change of the overall reaction will be the sum of these two reactions. So basically, let's say our initial state is here, carbon and O2, and our final state is here, carbon dioxide. So we can achieve this goal by using route 1, directed combustion. So we'll get a delta H, which is negative 394, which makes sense. The combustion is exothermic, right? But we can also do it, alternatively. We can first change part of the O2 into carbon monoxide, half of the O2 into carbon monoxide. And then we further combust the carbon monoxide in the second half mole of O2 to produce the CO2. So which means you use two steps to achieve the same goal, right? The overall goal is to convert carbon and O2 into carbon dioxide. So what is the meaning of Hess law? It states the delta H of this process equals to the delta H of the first step plus the delta H of the second step. So it's kind of, this is a wasting of time, right? It's so natural, right? But actually, this is built on is a state function, because if H is not a state function, this is not a valid, conclusion, right? Because the delta H is only related to the initial state and the final states. It's not related to what is the path, what are the routes to achieve, this goal, right? So we have negative 394 equals to question mark, which is root 2, the first step of root 2, plus negative 283, right? And then we can calculate the question mark. So I think you can calculate by yourself. The value should be negative, which also makes sense because carbon with oxygen to produce carbon monoxide actually is the incomplete combustion of carbon, right? Makes sense. And the second step is also exothermic because that is the combustion of carbon monoxide, right? So you can finish the calculation by yourself. And then I will leave you a question here. Can you guys calculate the question mark quickly? You may need to pay attention to the direction of the arrows. Yeah, mathematically, I think we can use a equation like this to finish the calculation, right? It shouldn't be, very hard. But a more practical way is to interpret the reaction in this way. So this is our initial state. This is our final state. What is the meaning of this process? This is how you convert, carbon, solid carbon, which is the major component of the coal, into some more useful stuff, such as hydrogen gas, right? You convert a solid fuel into a gas fuel, right? This is very important for a lot of countries, such as China, Germany, because those countries, I think including India, those countries, is rich in, coal, but there are not so much, natural gas or, oil in their land. So this is why they had, well-developed techniques to convert the solid fuel into the gas fuel, which is less pollutant, right? Which is also, higher in efficiency. So we can do it this way. First, we decompose the water into hydrogen gas and oxygen gas, and then we combine the carbon and the O2 turn into carbon dioxide. So, you can do it by 2 steps, but the goal is the same, is to convert, carbon into some gas fuels. Okay, this is the general idea of the Hess law. So by using the Hess law, we have an important conclusion. So if we know all of the molar enthalpy formation of the reactants and the products, we can use them to calculate the molar reaction enthalpy of the reaction. So you probably need to take a while to think about why this is correct. Let me show you an example. So let's say CH4, still O2, produce CO2 and water. So we use this example so many times already. So our goal is to calculate the molar enthalpy of the reaction, right? And now we know carbon plus 2H2. I will skip the states, okay? O2 into O2, carbon plus O2 into CO2, hydrogen gas plus O2 into water, but I need to times 2 because there are 2 moles of water. This is the 2 moles of, So which means this is the delta HF of CH4. This is the delta HF of O2. This is the delta HF of CO2. This is the delta HF of water times 2. So what I want to say is we can add all of those processes together to minus this process, and then we should get the delta HR, which means the delta HR equals to the delta HF of carbon dioxide times by 1, because the coefficient is 1, plus the delta HF of water times by 2, minus the delta HF of CH4 minus the delta HF of O2 times by 2, because there is a coefficient of 2. So this is exactly the application of the Hess law, because you can say our initial states are all those elements, right? And then the final states, you can make a circle by yourself to make a loop, right? And then you should get the results. So it changed into a final equation like this. It will take a while for you to fully prove it, but I think we just need to get a sense. You use the sum of the formation of the products minus the sum of all of the reactants, and actually it's built on the Hess law. And also pay attention, there is a coefficient. You need to multiply by the coefficient of each substance in the balanced chemical equation, right? So there is one question.
I had a question.
Yeah.
I noticed that you wrote delta HF instead of delta FHM. Like comparing that with the notation to the side, are they the same or?
Yeah. They're all the same. Sometimes if you do not want to write down the M, you put the R after the H. But if you want to show the M, you may have to put the R in front of the H. But they means the same stuff. By default, actually, all of the delta H are molar enthalpy change. Okay, let's have a look at this example. It might take a while, so I will not give you a poll. You guys can take 1 minute to try the method, and hopefully you can get the results. It's not so complicated. Remember, products minus reactants multiplied by the coefficient. I think the method is pretty straightforward, right? The calculation may take a while because it's so easy to make mistakes. Negative, minus, right? Multiplied by a certain coefficient, right? So it really requires you be very familiar with your calculator. You must be a very good friend with your calculator. But if you do not use your calculator, you can never be the friends with it. So this is why, keep practicing. This is like for the first time, how you to learn typing, right? It takes a while for you to know where is this key, where is that key. I remember, in the beginning when I tried to use a scientific calculator, it's so easy for you. You want to press 1 or 0, but it's so easy for you to press another key, right? So you may take a while to check it. So I think Alex, probably also had a strong impression, right? How to use the calculator. Oh, we have two Alexes here. Okay, you can check the answer by yourself because I listed the year here and the question number to check it by yourself. Okay. The next part is the estimation of the delta H by using the bound energy. For example, if we want to calculate the enthalpy change of this process, which is hydrogen gas combusted in chlorine gas to produce 2 mole of HCl, H2 plus Cl2 produce 2 mole HCl gas, right? How can we do this? We'll make a loop. This is my initial state. This is my final state. And then I will do it this way. First, I will decompose all of the molecules, break down the HH bond in hydrogen gas, break down the Cl-Cl bond in chlorine gas. So obviously, this process absorb energy, right? Because I need to break down bonds. So this is why there is a arrow towards up. And then we'll recombine the atoms. So the hydrogen will bind with the Cl to make a new HCl bond, which is here. And another hydrogen will bind another Cl to produce another molecule of HCl. So obviously, this process is exothermic, right? So the delta H of the reaction will equal to the energy needed for this process plus the energy needed for this process. You know, since the first process is endothermic, so it will be positive. So it will be the bond energy, which is broken. I should say the sum of the bond energy, right? And plus negative of the bond energy form, right? Because when a bond is formed, it will release energy. So this is why I add a negative sign here. And the bond energy is typically defined to be positive. Basically, it means how much energy needs to be absorbed to break down a certain bond. So I think the process is pretty straightforward, but sometimes it's easy to make mistakes. So the bond broken will absorb energy, so the sign will be positive. And the bond formed will release energy, the sign will be negative. So with this, I think we can take a very quick calculation for the example here. So we list all of the bond energy here. You need to calculate what is the delta H of the reaction. I will give you 1 minute, very quick calculation. Okay, I think all of you guys got the same answer, or except one. Yeah, I think A is the correct answer, right? We shouldn't make mistakes. You know, so many students make the same mistake. Hard to believe, although it's commonly happening in the US NCO. Sometimes you will see, you know, the correct percentage of a certain question is around 10 or 15%. That means the question is, you know, it's tricky. So most of students think in that way, and they strongly believe this should be the correct answer, but actually it's not. Okay, and then let's have a quick look at this question. Did you get the results? Is the answer C? Okay, yeah. Just want to remind you first, although it might be, wait a second, although it might be a little bit time consuming for you to write down the full equation, but I do believe this is very important. Don't save the time here because it's so easy to make mistakes if you forgot to multiply by the correct coefficient, right? And how can you get those equations? Only when you write down the balanced equation. Yeah, go ahead. What's your question?
Why don't you use the double?
Use the double bond for?
Yeah, I think it's D.
Oh,
Yeah, that's what I.
bad. My bad. You are so right. Okay. You are so right. So I think C is a tricked answer, right? And if you, it takes so much time. Finally, I got the correct answer. I feel so good, and I chose the answer. So you can never figure it out. This is a incorrect answer, right? This always, happens in the US, and so which means all of the answers are purposely designed, right? So it's kind of if you jump into this hole, you can never climb up because you will stay here forever. So this is very important for you to get it correct for the first time. Because I do believe even if you show your full work on your scratch paper, it's still very hard for you to find this mistake when you have the time to review it. Because for the first time you think about, and then you will accept it and think this is the correct way. Very good reminding. Thank you so much. So the answer will be D?
Yeah.
Right? Okay, thank you so much. There is the extension. So what is the molar enthalpy of reaction of the decomposition of 1 mole hydrogen peroxide using the data here? So I will try to not make the same mistakes this time. First, you need to know what is decomposition of hydrogen peroxide, right? Hydrogen peroxide is unstable. It will decompose into water and oxygen gas. This reaction is so commonly used for the elephant toothpaste, right? There is a Guinness record you can find from YouTube. So basically, they made a huge, several, I think maybe 10 meters high of the toothpaste, and it's like a rocket. So this is the reaction behind that. Yeah, let's try it. Did you get the same answer with me? Negative 100, 1.5 kilojoule per mole. Actually, you will realize the two HO bonds are broken in the hydrogen peroxide, and they are also formed when the water is produced, right? So actually, the net change is 1 OO single bond is changed into half of OO double bond. So it's a comparison between how strong is 2 OO single bond and 1 OO double bond. But the result is the OO double bond is much stronger than 2 times of the OO single bond. This is a great example of 1 plus 1 is greater than 2, right? And actually, this is a very, very interesting story. Why the OO double bond is so much stronger than 2 of the OO single bond? We will discuss, I think I already finished discussion in season 1. So probably you can think about, try to recall why it's like this. Back to this question. So since this bond is so strong, so it's exothermic. So it gave us a very, very useful conclusion is all of the peroxide with the OO single bonds are thermodynamically unstable because when it decomposes or it breaks, it will change into half of an OO double bond, which is much more stable than the OO single bond.
Oh, I have a question.
Yeah.
Why does it become water and O2 rather than maybe H2 and then O2?
Yeah, this is a good question. You can also check the delta H of the reaction if the product is H2 and O2 to see which one actually will release more energy. And then you'll get a sense. Because the reaction wants to go to the place with the lowest energy because they want to produce the most stable product, right? So if it's hydrogen gas and oxygen gas, you can double check the delta H by yourself. I don't think it will release so much energy anymore. So this is why it's water and O2, not hydrogen gas and O2. But it's a good question.
Okay, thank you.
Yeah, no problem. I will leave this question for your homework. That is not very hard. It's a direct application of the equation we just learned. So next part will be the delta C, which is combustion. Yeah, so if the standard enthalpy of combustion of those kind of stuff are those data respectively, I think we need to have a look at what the definition of combustion. For combustion is 1 mole of fuel produce the most stable oxide. Typically, a combustion is in oxygen gas, right? So for example, if it's graphite, it will be solid graphite turned into CO2 gas. If it's hydrogen gas, it will be liquid water, if we suppose it's also 25 degrees Celsius. If it's C3H8, it will be 3 moles of carbon dioxide plus 4 moles of liquid water, right? Change into. So this is the definition of combustion. 1 mole, 1 mole, 1 mole, 1 mole fuel, most stable oxide, right? All of the elements will change into oxide. Carbon will be carbon dioxide and hydrogen will be, water. Or you can say dihydrogen monoxide, but it's oxide, right? Okay, and then we need to use, those standard enthalpy of combustion to calculate the molar formation of the propane, which is C3H8. So by definition, it will be carbon, which is graphite, the most stable element of carbon is graphite, plus 4 moles of hydrogen gas, 3 moles of carbon, change into 1 mole of C3H8. Is this correct? We need to have 1 mole of final products from the elements, right? So we try to make a loop, make a cycle, because if we combust this into carbon dioxide, we combust this into water, and we combust this into carbon dioxide and water. So which means if this is our initial states, it will made by reaction 1, reaction 2, and reaction 3, right? because this actually equals to this. So the overall reaction will be 1 plus 2 plus 3. But when you say plus 3, actually plus 3 is the negative delta HC of C3H8. Make sense? Because the combustion is the opposite process. So I think you can easily get the delta R of the reaction equals to the delta F of C3H8 equals to delta H1 plus delta H2 minus delta H3, which will be the sum of the combustion enthalpy of the reactants minus the sum of the combustion enthalpy of the products, right? So it will be 3 times negative 393.5 plus 4 times negative 285.8 minus 1 times negative 2219.9. So you should get the final results. So you guys can check the answer by yourself.
Why is it not products minus reactants?
A very good point, right? This is something I want to further talk about. So if you remember, for formation, we use products minus the reactants, right? The equation is here. You use products, the sum of the products minus the sum of the reactants. But here is a different story. Is the sum of the reactants minus the sum of the products. Is this, is there a reason behind this, or is just a special case? We definitely can mathematically prove this, but I think you just need to get a feeling. Formation, your products, your substance is in the right side, is the products, right? That is the formation from the elements. And for combustion, the substance actually is in the reactant side. So this is why it's not products minus reactants anymore. It's the reactants minus the products. I didn't make it very clear, so you guys can further take some time after class to think about why these two equations will have a different direction, right? I can briefly talk about this, although it's already pretty messy. So let's say your initial is here. Initial is here. This is your initial, and your final is here. So this is the first way to actually do the combustion, but you can also do in this way, number 1, number 2, and these two are the same, and then number 3. So the overall process will be 1 plus 2 plus 3, but the 1, 2 are exactly the opposite direction of the formation, right? And the third reaction is the formation, right? So this is why you use products minus reactants. Okay, let me see. Since we took about 10 minutes to briefly introduce each of you, so we will use another 10 minutes to finish the class today. If we cannot finish all of the contents in the lecture notes, this happened so much in season 1, because I'm always too ambitious I want to give you a full story about what I want to express, give you a deep understanding about the contents. So this is why I cannot finish the contents for most of the class. So this is why we have the the open session for the molecular orbital theory. I think it will happen to season 2 as well, although I already tried my best to cut a lot of contents, but there is still a lot of information I want to deliver. So I will do it this way. So if you have to go right now, feel free to go. I will, you can ask me for the recording. You just need to kind of, drag to the, last 10 minutes for the content you missed, right? Take some time, to make it up. If we still cannot finish, I probably will record a short session, let's say 20 to 30 minutes, and I will share with you guys. But because I have to say, this lecture notes is the shortest and the simplest. The common lecture notes much more, difficult than this one. So I think this time we shouldn't do the survey after this class. I will, give you the survey probably, after the second or the third session, because that really represents what we are going to cover in the second season. Because the first one, after you guys will feel, it's just so, right? Not so hard. But after the second and the third one, it's not. I want to trick you because it always starts from the easy contents and then it goes harder. Okay. Feel free to go if you have to go, and then ask me for the recording. So I will continue. So the next part, finally, is called the first law of the thermodynamics. I think you all know the first law of thermodynamics, which is the conservation of the energy, right? That is the famous, quote, right? The energy will not be produced or, destroyed. It will just, change from one style to another style, from one substance to another substance, right? But in chemistry, we change it into a slightly different way. It's called the internal energy, which is delta U. Internal energy equals to the sum of Q and W. Q is the heat, W is the work. So basically, if a substance changes internal energy, there are only two possible ways. Either it transfers the heat to the others, or the other stuff transfer heat to the substance. W is the work. Basically, it's the system that work to the environment, or the environment that work to the system. There are the only two ways. So this is called the first law of thermodynamics. Please be aware, the U in the USNCO sometimes is use E. I should say for most fields they use E, but I want to differentiate from the U and the E. E is the general energy, but U is specific for internal energy. So internal energy is kind of how much energy is stored in the system. So it's different from the kinetic energy. It's different from the like the electric energy or any other form of energy. It's just called internal energy. So this is the U. And then finally, we can talk about the definition of the enthalpy. The enthalpy is defined in this way. This is the definition. So don't ask me why. So when it was invented, it defined in this way. The H is defined as the sum of the internal energy plus the pressure times the volume. So U plus PV is the enthalpy. So which means the delta H will be delta U plus delta PV. Makes sense, right? Well, this is still, by definition, it just change you a change. Delta H equals to delta U plus, delta PV. And then if P is a constant, we can further change this into delta H equals to delta U plus P times delta V. Make sense to you? Okay, and then if all of the gases are ideal, the P delta V based on the ideal gas law equals to the delta N RT. Delta N is the most change of the gas during the reaction. Does this still make sense to you? P delta V equals to delta N RT. So now let's have a look at this question. For which reaction is the delta H value close to the delta E value? Let's change this into delta U. It's the internal energy change. So basically it's asking which option have the minimum P delta V, right? In another word, it means which one has the smallest delta N regarding the gas change. So if we have a look at 1 and 2, this one is 1 mole of gas reacting with 2 mole of gas, produce 1 plus, this is the liquid. So the delta N here will be 1 minus 2 will be -2, right? It's still products minus reactants because it's final minus the initial, right? And the second one, the delta N will be, this is the gas, 2 plus 2 minus 1 minus 3 is 0. So I think the second reaction is actually what we are looking for, right? The delta N is 0, so which means the P delta V is 0. So the delta H will be close to the delta U. So the answer should be 2 only. I think this is just a conceptual question. You need to understand what is the definition of the H. Is U plus PV. Any question about this? Okay. And the next part is the volume work under constant pressure. We have to talk about the work is negative P delta V. And now we are going to talk about why it's like this. But by definition, work equals to force times distance, right? Can you guys recall what is the definition of pressure? Pressure by definition is the force over the area, right? It's kind of, how much force per unit of area, right? So if we change the force into the pressure times the area, right? Because this is definition of the force, and then times the d, the distance. So let's have a look at the container. So we have some gas initially like this, and then there is a volume expansion. So the pressure will equal to the external pressure. So let's say it expands, very slowly. Let's keep the internal pressure always the same as the external pressure. So the pressure will be the EXT, which is the external pressure. And then the distance will be here. And then the area of this circle times the distance will be the delta V. So finally, we change into P times delta V. But, since when the gas is expanded, the system does work to the environment. So which means the system will lose energy. So this is why we have a negative sign. We have negative sign because the force actually is in this direction, but the distance is in this direction. They have different, direction. They are both vectors. So in physics, if they have different direction, we need to have a negative sign here. So you can have a different way to interpret why there is a negative sign. I will like you guys try to think about when the system is expanding, the gas is expanding, the gas does work to the environment. So this is why the system will have a smaller internal energy based on the equation here, if the work is negative, right? So you need to get a negative work if the gas is expanding. So this is why there is a negative sign. Okay, so this is not a negative sign. This is just, a short line, okay? So W equals to negative P external times delta V. And we can further change this into delta nRT if we keep the negative sign here. This is called the volume work under constant pressure. Let's have a quick look about this example. I probably will end the formal session today in 5 minutes, and then I will make about probably 30 minutes of recording for the remaining parts and share with you hopefully before Friday. This is not an easy question. There are a few points you need to pay attention. First, we can calculate the delta N to be +3. This is pretty straightforward, right? But you still need to calculate, how many moles of gas is produced, because the delta N should be the increase of the moles of the gas, right? So this is why I have this calculation. 1 gram divided by the molar mass, we get the moles of the reactants, which is the sodium azide. And then I multiply by 3 and divided by 2. Why I need to do this? Because every 2 mole of reactants will produce 3 mole of gas. So this will be the moles of the gas, right? The delta N. And then you multiply by R. Please be aware, there are so many different R's, right? With different unit and different value, but you have to use the one which is 8.314, because that is the only one has a unit of joule, right? You want to calculate the work. The work has a unit of joule, so this is why you must use this. And then you multiply the temperature, so you can see the units are perfectly, canceled with each other. And the only remaining unit is the joule. If I didn't remember wrong, the value is 57.2 joule. So you can further check by yourself, but this is not the key point. The key point is whether the answer is B or D, right? Because there is only a difference of sign. Alex, did you remember we had a discussion about this, right? Did we?
Yeah.
Did you remember, what is the answer? But the question is asking how much work is done by the gas.
I think it was like Danny. He was like complaining about how it should be D, but the answer itself was B, because obviously the gas does the work and loses energy.
This is tricky. It's an expansion. So based on our discussion, the work is negative or should be negative. But the wording here is very interesting. It's asking how much work is done by the gas. So The answer is B, because this is exactly the work done by the gas, although the system, lose energy because the gas did the work, right? This is a little bit, advanced question. It's from the national exam. It's both a combination of conceptual understanding and also the calculation. So pay attention, the delta N here should be the increasement of the gas molecules.
And what does the R and the nRT stand for? Delta
The
N?
R is the ideal gas constant. You know the PV nRT, the ideal gas law, right?
Mm.
If you check the R, there are different combinations with different units. For example, if you use, kilopascal for the pressure, use, liter for the volume, you get an R. But if you change the unit of the pressure and the volume, you might get a different R with a different value and different unit, right? So this is why it's always confusing. But in thermodynamics, or any content we are going to learn, I will strongly recommend you to only use this. So this is why when I calculate the gas law related questions, I always convert every volume or pressure into the one I want, because I want to use the 8.314. Because in thermodynamics, we need to use the unit of joule. And this is the only one which can give you the joule. The others will give you a combination of like ATM times liter, or bar times liter, or other stuff. If you are not very familiar with the PV nRT, yeah, you need to find the related topics from your textbook. It was covered in season 1. Okay, do you guys have about maybe 2 or 3 minutes for me to finish 3.3? Okay, great, thank you. I apologize for the delay. Next is a very important conclusion. Delta H equals to QP, delta U equals to QV. We need to derive this equation by using the definition of the enthalpy. I will walk with you. So H equals to U plus PV. So delta H will equal to delta U plus delta PV. And then if we suppose P is constant, we change delta H into delta U plus P delta V, right? Does this make sense to you? And then we realize P delta V is negative W. Because W equals to negative P delta V, right? So we got this. And then according to the first law of thermodynamics, delta U equals to Q plus W, which means Q equals to delta U minus W. So we will replace the Q here. So this one will equals to Q, because delta U minus W is Q. Delta U equals to Q plus W, right? And since it at a constant pressure, so I can add a subscript P to this Q. So what does it mean? It means the delta H equals to the heat at a constant, measured at a constant pressure. What can we further interpret? It means delta H does not equal to Q at any moment, only when the pressure is a constant, right? Because it equals to QP. And later you will see the delta U equals to QV. So if you measure the Q, the heat at a constant volume is not delta H, actually is the internal energy change, is not the enthalpy change. So how can we get this? We still use the definition. equals to Q plus W. But if the volume is constant, and then the Q is 0, right? If there's no volume change, there's no volume work. So it just changed into Q. And since the volume is a constant, we add a subscript of V. So this means delta U is QV. So I would recommend you to derive those two equations by yourself after class again until you have your own understanding. Because this is, in college, this part is also confusing because this is part of physical chemistry. It's not even in the first year of general chem. But the USNCO is getting, very advanced. They always want to assess your conception understanding in this part, especially in the national exam. But those kind of questions, also appeared, in the local exam, especially in the recent years. You will see the trends. So finally, I want to turn back to the, calorimeter, the two types of the calorimeter we mentioned in the beginning. So both of these two types of calorimeter measure the heat. Can you tell me which one measure the QP, which one measure the QV? Which Q is under constant pressure? Which Q is under constant volume?
The coffee cup seems to be at constant pressure because it's always at whatever pressure of the room is, but the bomb is QV.
Yeah. Constant volume, right? Because it's in a bomb, it's a sealed container, right? It's a rigid container. So actually, this is why we can use the coffee cup calorimeter to get the delta H, because QP is the delta H. And by using the bomb calorimeter, when we measure the heat, it's not the delta H, it's the delta U. And the delta H and delta U has a difference of the work, right? That is the definition, because H equals to U plus PV, right? This is the definition.
Hey, Dr. Chen.
Yeah.
I have a question, which is like, isn't it also true that delta H is also equal to QV?
Delta H equals to what?
QV.
No.
Like if you do the equation, wouldn't work for both be 0? So it'd just be Q.
I don't think so. How can you get that? Yeah, maybe like you can send your work to me after class. I can check with you, and maybe I can share with everyone next time if we got some conclusion about this.
Okay,
thank you. Okay, one last question here. Is Q a state function? How about H? H we already confirmed is a state function, right? Is a Q a state function? And we already answered this question. We know how to match QP and QV. Okay, guys, have a look at this equation, the first law of thermodynamics. Obviously, the internal energy is a state function, right? And we already approved W is not a state function because it's path dependent. So based on this, the sum of Q and W is a state function, and one of them is not a state function. Can you conclude whether Q is a state function or not? It should not be a state function, right? Otherwise, a state function plus a non-state function definitely will give you a non-state function, right? So this is very interesting. Two non-state functions add together give you a state function. As you probably see, the last few pages were added by me in the last few days when I prepared for the lecture notes. So which means I do have an estimation about, I need to use about 2 hours, actually longer than 2 hours to finish the first 8 pages. I think, our pace is not too slow, right? Maybe it's okay or a little bit, fast, but still, the reason I put here is because I already finished, 7 of the 10 lecture notes, and I realized there are too much left. So I have to put some part of thermodynamics contents into the first one, thermochemistry. So this part will be in a, separated recorded video. And if you have any question, feel free, to let me know either by email or, we have a Discord server. I didn't get the time, to introduce you the server. If you like the social media, like Discord server, feel free to use that. Yeah, I'm active, in the server as well. Now 7:24, but pretty much, a lot of hours online every day. Email, Google Classroom, Discord, either is fine for me. I will frequently check all of the platforms. I will encourage you to ask questions if you have. Yeah, I think that's pretty much I have today. Really appreciate you guys can stay until the last second. I apologize if we use too much time today. Yeah, let's stop here. I will see you next Sunday. And check your problem set in Google Classroom. The problem set will only be shared in Google Classroom. If you didn't join the Google Classroom yet, please join, as soon as possible. And you can scan your worksheet and then submit in Google Classroom. And then that is the best way for me to provide you feedback. Okay. How do you feel in general? Any quick feedback to me? Good, Joy? Is there any complaint, such as too fast or too tiring? Okay, it will not be easy, definitely. But I hope you follow the class, you enjoy the class today. I need to kind of make a balance between the speed and the contents I want to finish. Yes, I will. Alex will send you the survey probably after the second or the third session, and then I will get some feedback from you guys, and then which I think it should be very important for me to further improve our teaching. I also got some really good feedback from students from season 1. I already kind of put some of the suggestion from them into the designing of the season 2, but it will take some time. You guys will see the difference. Great. Have a great evening. See you. Bye-bye.